So we're done essentially now with Newton's second law. It comes up once in a while here during the energy part, but we're done kind of working on it all for its own sake at this point. Okay, so now we're going to look at work and energy. And the good news here is that there's really not a lot different from what you learned about work energy theorem in Science 10. Okay, we get a little bit more complex in terms of the examples and problems that we go over, but okay, nothing has changed in the work energy theorem in physics in 100 years. Okay, it's still the same thing that it was. It still works the same. Okay, so we don't have to worry about so much learning a brand new concept. We're just going to review it quickly and then look at some kind of more in-depth applications of it. All right, so big things we have to know here. What is work? Okay, work is a what? No, that's a force. The force is a push or a pull in any direction. Okay, work changes something. What does work change? Might be the other part of the title. It's a change in energy. Okay, this is what we need to know. Work is a change in mechanical energy. That could be potential energy. That could be gravitational potential energy, elastic potential energy, okay, kinetic energy, or all of them. Okay, anytime we do work, we are changing the mechanical energy of the object. Okay, in Science 10, we only did examples where work changed either kinetic or potential. We never did any where it changed both at the same time. Spoiler alert, now we're going to do some where both change at the same time. It's really not all that much difference, not really any huge amount harder or anything like that. Okay, so work is first off a change in mechanical energy, and we can calculate that as well by multiplying force times distance. All right, that is what we learned in Science 10. Okay, understand the relationship between force and work. Well, that has to do with this part here. Okay, if I double the force over the same distance, how much more work will I do? Twice as much. It's a linear relationship. If I push twice as hard, I'm going to do twice as much work. Okay. All right, and learn that depending on the situation, work and energy can be equal. Okay, because work is a change in energy. If I started out with no energy, the amount of work that I do will equal the new amount of energy the system or object would possess. Okay, but work is always going to equal the amount of change in energy that an object or system experiences. All right, questions on that so far? Because hopefully that sounds familiar. All right, so strictly speaking, work is done anytime a force causes an object to move through a distance. If the object doesn't move, then no work is done because it is impossible to change the energy, the mechanical energy, of an object without it moving. All right, everyone kind of follow me there. All right, if I push on this wall, okay, maybe it does get a little bit of energy. It does move a little bit. I feel huge right now. Okay, so if I push on this wall, am I doing any work on the wall? No, okay, I'm not. Well, maybe I changed its shape a little bit, but okay, probably not. If I push on it, it doesn't gain any kinetic energy because I don't make the wall move any faster. It doesn't gain any potential energy because it doesn't get any higher off the ground. Okay, it doesn't gain any elastic potential energy because I can't like compress it and have it fly back at me, or anything like that. I didn't do any work on the wall. Right. The weird part of that, though, is that if I continue to push on the wall, I'll get tired. Why would I get tired if I'm not doing any work? I'm still applying a force, but if the wall's not changing in energy, why am I losing energy? Why am I getting tired? Because the wall pushes back on me. It's a Newton's third law thing. Okay. When I push on the wall pushes back, and my muscles, when I exert a force with them, contract. That is, they shorten. Okay. There's the distance over which the force returning to me is acting. I have to thus brace myself or I'll fall over backwards, and as a result, I expend energy in response to the force coming back on me. All right, so even though I don't actually do any work on the wall, I'm still expending energy and bracing myself against the returning force from the wall. All right, if My car stalls, or like what happened to Mr. Real over the Easter break, he lost reverse in his car. Okay, I may have to push it in some direction. Okay, that is going to require me to do work because I'm going to change the energy of the stalled car. When it's stalled, it doesn't go anywhere. Okay, if I get it moving, I am changing its kinetic energy. Right, I'm changing its velocity from 0 to whatever velocity I can push it to, and as a result, okay, the car will gain kinetic energy, and it'll gain as much kinetic energy as I can do work on it. Once I stop doing work, then the car doesn't gain any more energy. Everybody all right with that? Okay. So in this diagram here, okay, the force and the displacement are in the same direction. We can see that the force is horizontal, okay, and the displacement is also horizontal, right? So calculating the work done would be as simple as just going work equals force times distance, like we would have in Science 10, right? But you can see here that we've changed the formula slightly. Even though we almost never use it in this form, it is valuable to understand why it's written with that cos theta thing in the middle. Okay, and the reason for that is this. If you recall, back in Newton's second law, when we dealt with forces, okay, that were angled like this, but the object moved horizontally, okay, let's say that this is 200 newtons worth of force. Is that 200 newtons doing all the work? Right? Because part of this 200 newtons is vertical, and the object's not moving vertically. So that component of this 200 newtons isn't doing any work. Okay, but this component of the 200 newtons is doing some work. All right, so if this angle here was, I don't know, let's say 30 degrees, okay, then this side of the triangle would represent the force that changes the energy of this object, because the change in energy is this way. Right? Its change in velocity is horizontal, right? Even though work is scalar, the change in velocity is still a vector quantity, okay? And we would be looking at only the part of the force that actually does work, that is, moves in the direction the object moves. So that's where this cos theta thing comes in, okay? We would calculate the work done by taking this force, the 200 newtons, okay, multiplying it by the cos of 30 degrees, okay, and then over whatever distance we were to pull the object. Right? That would tell us the amount of work done in pulling the object in that direction. Okay. Everybody all right with that idea? We very rarely use the cos theta part, but we still have to understand why it applies. Okay, so the units of work are a Newton meter because, well, we're multiplying force times distance, and the units for force are Newton, and the units for distance are a meter, so Newton meters. Okay. Broken down even further, okay, that would be a kilogram meter squared per second squared, because a Newton is a kilogram meter per second squared. So a joule, which are the units for energy, is a kilogram meter squared per second squared. You never have to write it that way, just write it as joules, right? But if you have to do any dividing or multiplying or anything like that, you may need to know what the units are. Okay, questions on that one? All right, so those 4 girls there that are pushing on that rock, and they're not pushing very hard, but they're pushing, okay? Are they doing any work? Well, they're not moving the rock, so they're not doing any work on the rock, okay? Is work being done? Possibly, yeah, okay? I mean, they're going to expend energy pushing on the rock, right? And so we could say that certainly, yes, the rock is not having any work done on it, but there could still be work in the system, okay? Their muscles are going to shorten because they contract when they use them, things like that. Okay, so if you push on a rock for all eternity, okay, it won't make any difference. You won't accomplish any work, okay, because technically you don't move the rock. All right, now this has to go back to our force cos theta thing. Okay, often the force and the displacement do not point in the same direction. So if you've got like a luggage carrier, okay, or you've got one of those suitcases with the wheels on it, right, that you pull at an angle, okay, you are pulling this direction, but the cart is moving this direction. So again, only the horizontal component of your force is actually doing any work, because you're not changing the potential energy of the luggage carrier or suitcase, because you're not lifting it off the ground, right? Now, if I'm doing work, okay, in this direction here, that work could come in two forms. I could either be accelerating the luggage carrier, that is making it go faster, or I could be carrying the luggage carrier at a constant velocity. Now, if the velocity is not changing and the potential energy is not changing, am I doing any work? Okay, it would seem like I'm not. I'm certainly not changing the energy of the luggage, but I'm still doing work. Work against what force? Well, again, I'm not doing any work against gravity because I'm not changing the potential energy, right? I would only be doing work against gravity if I lifted it up, okay? But I would be doing work against a force that's always present and always working against us. Friction, yeah, okay? And I maybe can't see the results of that, okay? But it could be measured. Your suitcase makes noise when you pull it along the floor, okay? The wheels make noise, there's drag, okay? That means that some of the energy of my pulling is being turned into sound. Some of it's also being turned into heat and other non-useful forms of energy, okay? That still represents a loss of energy from me. That's work, okay? Any change in energy is work, positive or negative. From my point of view, I'm doing negative work because I'm losing energy to now the surroundings. Okay? It's becoming sound and heat and other forms of energy that don't do useful work. All right, everybody okay with that? Okay, so just because an object doesn't change kinetic energy or doesn't change potential energy doesn't mean there isn't work being done, just not being done on that object. All right, everybody okay with that? It's a bit esoteric, but yeah. All right. So let's look at this example here so we see how this F cos of theta times d thing works. So let's say that the force in this handle of the luggage carrier, okay, is 45 newtons, okay, and she's pulling it at a 50-degree angle for a distance of 75 meters. All right, so we're trying to find the work. We know the force is 45 newtons. We know the angle is 50 degrees, and we know we're pulling at 75 meters, so we just have to plug in the numbers. 45 times the cos of 50 times 75. All right, so in your calculator, okay, you gotta remember to put that in scientific notation. So, or sorry, your answer will come out probably that way. So we got 45, okay, times the cos of 50 degrees, okay, times 75 meters. All right, so we get 2.17 times 10 to the 3. What are the units again? What does J stand for? Joules. Okay. All right, everybody okay with that? It's not anything really terribly difficult. It's just adding one extra little thing in there. All right, let's look at this example here. So I've got this person who's doing bench press. Okay, we want to determine the work done on a 710 Newton barbell if it's lifted at a constant velocity, so I'm not accelerating it, okay, 0.65 meters, and the work done when it's lowered. All right, if it's moving at a constant velocity upwards, what kind of energy am I changing about it? I'm changing its potential energy. Right. All right. So in this case, we have that the work done is the change in potential energy of the barbell. Now, they told me the barbell is 710 newtons, which means they told me the what of the barbell? Mass or weight? They told me the weight. All right. Weight is m times g. Anyone remember what the formula for gravitational potential energy is? M times g times h. Okay, so we just said that work can be calculated by going force times distance. When we're working against gravity, that's m times g against the force of gravity, and a vertical distance is known as a height. So m times g times h is just force times distance vertically. Okay. All right, so I want to calculate the work done when I lift it 0.65 meters. Okay, so we're going to take our m times g, which they gave us, 710 newtons, okay, and multiply that by 0.65. That'll give us the work done in lifting the barbell. All right, so this would require 400 or 4.6 times 10 to the 2, because I only have two significant figures there, 4.6 times 10 to the 2 joules worth of work. All right? And that is how much energy the 710 Newton barbell now has as you hold it triumphantly at arm's length. If something has potential energy, what can it do? Yeah, it can fall. And as it falls, it'll change its potential energy into kinetic. And anything it hits along the way, it will do work on, because energy is the ability to do work. Work could involve changing the energy of something else or changing its shape. You don't want it to change your shape. Okay, 461 joules is a fair amount of energy, and if it landed on your chest, it could break your ribs or your sternum or something like that. Or if it fell on your neck, it could be worse. Okay, we wouldn't want that, obviously. So you should always work out with a spotter. There's your life lesson for the day. Okay, don't do bench press with heavy weights by yourself. Okay, all right. So I now have this 710 Newton barbell at arm's length above me. Now I want to lower it back down. Now, if you're like so many people who I watch work out, you have no idea how to properly work out. So many of you I watch. Okay, so they do all this work in lifting the barbell, and then they just like boom, let the barbell come down really, really fast. Okay, are you getting anything out of the lowering phase then? No. If you want to get a benefit out of your workout, okay, you push the barbell up and you lower it back down at the same rate. Okay, that way you have to push hard, just as hard to lower it as you had to push to raise it. Okay, and you get way more out of the workout that way. Now, what that means though is that if I'm going to lower this thing back down, it's now going to do what with all the energy it had? It's going to, when it's back down here at a height of 0, it's going to have no energy. Where did all that energy go? Yeah, into me. I actually have to absorb that energy back. Okay, and that's why we want to push upwards as we lower. Okay, it's going to change the shape of my muscles as I lower it. Okay, and so I get a benefit out of it in both directions. Does that sort of make sense to everybody? All right, so the work then from the barbell's point of view, when I raise it, would be positive. Okay, so as I raise the barbell, okay, I'm going to have positive 4.6 times 10 to the 2 joules worth of work. But when I lower it, from the barbell's point of view, it's lost that energy. And we can prove that mathematically using the formula. Sorry, Austin? I'm not giving it direction. I'm giving it whether it was gained or lost. Okay, so yeah, you're right. It seems like work is scalar, but I'm assigning a direction. I'm not assigning a direction. I'm assigning gain or loss. Yeah. Okay, so if I look at the formula here, work is F times the cos of theta times D. Okay, when I'm lifting the barbell, the angle is 0. The force and the direction the barbell moves are the same direction. They're both up. But when I lower it, the force exerted is up, and the direction is 180 degrees to that, because it's going backwards. Okay, so if I'm looking at the trajectory of the barbell here, okay, that way's up. Okay, this is 180 degrees if I'm lowering it back down. So what's the cos of 180 on your calculator? Nope, not of 18, 180. -1. So everything else is the same. I still push upwards with 710 newtons. I still lower it 0.65 meters, but now I get a negative work because now the barbell has lost energy. It's lost potential energy because it's returned back down to a height of 0. Okay, questions on that? Everybody's okay with that idea that work can be positive and negative even though it's a scalar quantity? Okay, because sometimes people struggle with that. Okay, so work is scalar. Okay, work does not have direction. Once energy is transferred, it can be used, okay, to do whatever we want in whatever direction we want. All right. So this is what we just talked about here. Okay, there's no acceleration, so we're only changing the potential energy of the barbell. So the force is 710 newtons. Okay, and then when we lower it back down, the angle is 180 degrees, so we get negative 460. Okay, on that one. All right. So things to remember here about work and energy. In order to do work, you have to have energy. You can't give away what you don't have. All right, energy is not like money. Even though technically money should work like energy, you shouldn't be able to give it away if you don't have it, but whatever. Banks say you can, okay? Because they get interest when you go in the hole, right? So with energy though, if I don't have any energy, I can't do any work because work is a transfer of energy and I can't transfer what I don't have. Everybody all right with that concept? Okay. So in the perfect world, which is what we're going to operate in, okay, all the energy that I have is going to do useful work. We're going to consider that everything is 100% efficient and no energy is lost to the surroundings. Okay, thus either kinetic or potential energy is numerically equal to the work that's done. Okay, so if I do 200 joules worth of work, I'm going to change the mechanical energy by 200 joules. Okay. All right, that is what we call the work energy theorem, and that is probably the most important concept in high school physics. Okay, it just comes up everywhere because, well, energy is the reason things happen, right? If we didn't have energy, stuff wouldn't happen. All right, so basically it says that energy is needed to do work because work is a transfer of energy, okay? And energy is gained or lost while work is done. Okay, things to remember here as well from Science 10. The formulas for kinetic and potential energy. Okay, we already looked at the one for potential energy. It's the force of gravity times the vertical distance, m times g times h. Okay, for kinetic energy, we are looking at 1/2 mv squared. Okay, so we're taking the mass and we're multiplying by the speed of the object squared. All right, now we just said that a joule is a kilogram meter squared per second squared. Okay, obviously this is going to get us those units, okay, because we're going to be taking mass in kilograms, multiplying by acceleration due to gravity, which is meters per second squared, and then multiplying by height, which is meters, so that'll give us the right units. Okay, in this formula here, we're taking mass in kilograms, and we're multiplying it by speed squared. Well, the units for speed are meters per second, the units for speed squared are kilogram meters squared per second squared, so both of those formulas do arrive at joules for their units. All right, and we said here that work is a change in mechanical energy. So something else we have to remember from Science 10 is that mechanical energy is the sum of both potential and kinetic energies. All right, is that ringing a bell from Science 10 as well? Okay. All right, so we're going to look at a few examples here, just kind of refresh our memory and then kind of start building on it for Physics 20. Okay, we'll see how we go here. Except we're not going to do that one because it's using rectangular coordinates. Okay. All right, let's look at, actually, you know what, we can do all of these ones. We'll walk through number 1 together, and then I'll have you do 2, 3, and 4. All right, so on number 1, we have a sled being pulled along a horizontal surface. Okay, with a force of 620 newtons at an angle of 42 degrees above the horizontal. Okay, but it does say it's being pulled along a horizontal surface, which means it's moving horizontally. Okay, how much work is done to pull the sled 160 meters? Right, so we're told that the distance is 160 meters. All right, work is F times the cos of theta times D. All right, so we're just plugging into this formula here for number 1. So the force is 620, okay, times the cos of 42 times 160 meters. Whoop. All right, so 620 times the cos of 42 times 160. All right, so we got 73,719 joules. Okay, so we'll go with 7.37 because we have three significant figures here. 7.37 times 10 to the 4 joules. Generally, we don't use kilojoules, but yeah, you could. It would still be correct as long as you shifted the decimal over. All right, here's where I would say we would take another, this would be like something you did in Science 10. Okay, I would now ask you, if there was no friction, how fast is the box go, or is the sled going after this work has been done? All right, so since it's being pulled horizontally, we know its potential energy is not changing because its height is staying at ground level. Everybody okay with that? So the only kind of energy then that's changing is our kinetic energy. So we can then say that the work being done is changing only the kinetic energy of the box. Now, if we assume it started from rest, that means that the work we just calculated equals EK final minus EK initial. Okay, change is always final minus initial, whatever you're dealing with, this, okay, you just put it in there. All right, so this is going to be our final kinetic energy because that's what we have after the work is done. And we said we started from rest, which means EKI is 0. All right, so then what I can say is that work equals 1/2 mvf squared. Okay, because the formula for kinetic energy is 1/2 mv squared. If I want to figure out how fast this object is going, okay, I need to know its mass, don't I? Did the question ever give me that? That's what makes it a bad question. Okay? You should always give the mass so that teachers can expand on a question. We can't go any further than that now. But if we had the mass, okay, could we solve for VF? Right? We just manipulate, bring half of m over and square root, and we would be there. You did a whole bunch like that in Science 10. Okay? Lots and lots of them. All right, let's have you guys try number 2. Okay, actually try 2 and 3 for right now. All right, so we have a force that acts at an angle of 30 degrees relative to the direction of displacement. Okay, we're looking for what is this force? Okay, if it's going to do 9,600 joules worth of work, okay, over a displacement of 25 meters. All right, so work equals F times the cos of theta times d. We're looking for F. So basically all we have to do is divide both sides by the cos of theta times d so we can bring it over here. Okay, that'll leave us with force, and then we just have to plug in our numbers. When we plug it into our calculator, the bottom does have to be in brackets, otherwise our calculator won't spit out the right answer. Okay, 9,600 joules divided by the cos of 30 times 24 meters. Sorry, 24 meters. Sorry, it was 25 meters, wasn't it? Okay. All right, so when we do that here, okay, we'll have our 9,600 joules divided by, in brackets, the cos of 30, okay, times 25. All right, 443 newtons, okay, which is what they've got there. All right, how many people are done number 3? Okay, do we need to go over number 3 as well? Yes. Okay. All right, so on number 3, we're told the force is 640 newtons and it's doing 12,500 joules worth of work over a displacement of 24 meters. Okay, so what we don't know is what theta is. So we know this is 640 newtons. We know that the work done is 12,500 joules. Okay, we are just looking, and that is over 24 meters. So we're just looking for what theta is. So similar thing here, okay, work is F times the cos of theta times d. So if I want to get theta by itself, I'm going to divide both sides by force and distance. So I'll have work over FD equals the cos of theta, and then I just go cos to the minus 1 in order to get theta on the other side. Okay, so it just becomes a trig thing. All right, so we would have cos to the minus 1 of our 12,500, whoop, just the 5. Okay, divided by, and then I have to have the bottom bracketed, so that would be 640 times 24. All right, so the angle is 35.5 degrees. Okay. All right, how many people are done number 4? Okay, keep going on number 4. I'll give you a few more minutes on that one. 4 is more of a Science 10 work energy theorem question. The whole angle thing that we've just been working on for the last 3 questions basically makes no difference on this one. Okay, if you fall 20 meters, the potential energy you had 20 meters higher than you are after you fall is equal to the amount of kinetic energy you have at the bottom. Agreed? Okay. So when you're falling, what force is doing the work on you? Gravity, because it's converting the potential energy you had from whatever height you were at into kinetic energy, right? Remember, work is a change in energy. Changing one form of energy to another still counts as work, right? And so that's what gravity does. As you fall, it converts your potential energy into kinetic energy, all right? So if I want to calculate how much work gravity did before the bungee cord starts to stretch, okay, I just need to know, because that will be the change in energy, which is the work done. Okay? The change in potential energy will be the work gravity did while the person fell 20 meters. So all I have to do is take the 60 kilograms times 9.81 times 20 meters, okay, and that should come out to this number, 1.8 times 10 to the 4 joules. No, because the person's not losing or gaining mechanical energy in this case. Their mechanical energy is staying the same. It's just being turned from potential to kinetic. Okay? If they were, like, once the bungee cord starts to pull, then the energy becomes negative, because now they're transferring the energy to the bungee cord and changing its shape, lengthening it out. Okay? But something falling isn't losing mechanical energy. That's that conservation of energy thing we talked about in Science 10, right? EI equals EF, all the roller coaster questions that you would have done. Okay, that's that idea. You're not doing any work because your total energy remains the same. All right. Now, work can be done when both potential and kinetic energy change. All right, so this is going to be our first example of something a little more in depth than what we would have done in Science 10. Okay? In this case, I have a block that's moved up a frictionless incline by a force that's parallel to the plane. Okay, so this applied force is the force they're talking about right there. Okay? At the foot of the incline, so where the height is 0, okay, the block is moving at 1 meter per second. At the top of the incline, which is 8.50 meters higher than the lower end, okay, the block is moving at 4 meters per second. So I'm accelerating this block uphill, which means I'm changing both its kinetic energy, because I'm making it go faster, and its potential energy. I'm changing both here. All right. So back in Science 10, okay, when we were doing problems like this, okay, we only ever dealt with work being a change in either kinetic or potential, when in actual fact, work is the change in mechanical energy. All right. So a problem like this can be expanded out like so. Mechanical energy is the sum of both potential and kinetic, okay? And we know that delta means final minus initial. So the mechanical energy final minus the mechanical energy initial. And we can calculate mechanical energy by adding together potential and kinetic. Okay, so these 3 things are saying exactly the same thing. Work is a change in mechanical energy. Okay, change means final mechanical minus initial mechanical. And mechanical energy is the sum of the potential and the kinetic at each point. Okay, so what I'm saying here is, if I add the final potential and the final kinetic, that will give me this. And if I add the initial potential and the initial kinetic, that will tell me the initial mechanical energy. Everybody all right with that idea? Okay. Now we have to go back to our block here. This question starts, so the initial point is the bottom of the ramp. How much potential energy do I have at the bottom? None. All right, so which one of these energies here can I take right off? I can take off initial potential. Okay, since we're at the bottom of the hill, I don't have any potential energy initially. Okay? I only have the initial kinetic energy where I was moving at 1 meter per second. Right? At the top of the ramp, I've got potential energy and I've got kinetic energy because I'm actually moving faster. The question told me that. Everyone okay with that so far? Okay. Do I have formulas for potential and kinetic energy? We learned them back in Science 10. I can calculate potential energy by going m times g times h. And this will be the final height. In this question, that's 0.850 meters. All right, then I'm going to add the final kinetic energy. Kinetic energy is 1/2 mvf squared. Okay, so my final speed at the top of the ramp. Okay, I'm going to subtract from that the energy I had at the bottom of the ramp. 1/2 mvi squared. All right, so this is the energy here, okay, that I have at the top. Okay, and this is the energy that I have at the bottom. Okay, so I'm subtracting the energy I have at the top, I'm taking the energy I have at the top and subtracting the energy at the bottom because that'll tell me how much more energy I have at the top. That would have to be the amount of work done to accelerate the block up the ramp. Everybody all right with my logic there? Okay, I am changing the energy of the block. I'm increasing the energy of the block by accelerating it up the ramp. Okay, so now I need some numbers. Okay, I'm at the point now where I plug everything in, looking for the work done. Okay, so the mass of the block is 1.2 kilograms. Okay. All right, so I'm going to have 1.2 kilograms. Okay, so I'm taking my mass, multiplying by g, 9.81, and the final height, which was 0.850 meters. I'm going to add to that my kinetic energy at the top, which will be 1/2 times the mass, 1.2, times 4 squared, because they said in the question I'm moving at 4 meters per second at the top of the ramp. And then I'm going to subtract from that the energy I had at the bottom of the ramp, which was all kinetic. So 1/2 times 1.2 times 1 squared. Okay. Did I have very much energy at the bottom of the ramp? No, wasn't moving very fast. Okay, had no potential energy. All right, so let's see what that looks like here. So we have 1.2 kilograms times 9.81 times 0.850. That's my final potential energy. I'm going to add to that 0.5 times 1.2 times 16, 4 squared. All right, so there's my final mechanical energy. That's the energy I have at the top of the ramp, potential plus kinetic. Now I'm going to subtract from that the energy I had at the bottom. So 0.5 times 1.2 times 1 squared is 1, so I'm just going to leave it as 1. Okay. All right, so 19 joules worth of work is what's going to be required to accelerate that block up that frictionless ramp. Okay, so all we've really done different from Science 10 is that instead of just having this be final potential minus initial potential or final kinetic minus initial kinetic, it's now mechanical minus mechanical. Okay, we're using both types of energy. So while there's a few more numbers to plug in, the principle is still the same. Work is a change in energy final minus initial. Okay. I want you guys to try 1 and 2 for right now. I'll make them bigger so you can read them better. So on number 1, I've got this mountain climber who rappels down the face of a cliff that's 25 meters high. Okay, their mass is 72 kilograms. When they get to the bottom, they're only moving at 5 meters per second. If they'd have fallen off the cliff, would they be moving faster than that? Yeah, a lot faster. So obviously the rope is taking away some of their energy. Okay, they're doing work on the rope as they go down. Right? If you've ever held onto a rope as you fell, okay, or slid down the rope with bare hands, you get rope burn. Okay, that is you changing your mechanical energy into heat, and it equals sore hands. Okay, so this is kind of looking at that, except you'd be using climbing equipment. Okay, you let the what do they call them? Carabiners do all the work. Okay, the heat then ends up in the metal of the carabiner instead. All right, so we have then that work equals the final mechanical energy. I should write the EMF. Okay, the final mechanical energy minus the initial mechanical energy. All right, at the bottom, my mechanical energy is all in what form? What's my height at the bottom? 0, right? Do I have any potential energy at the bottom of anything? No. Okay, so I have no potential energy there. So if I'm looking at this and saying I've got EP final plus EK final, okay, minus EP initial plus EK initial, okay, so there's mechanical energy minus mechanical energy. My final potential is 0, so I can get rid of that. And what's which other one can I cancel off here? Initial kinetic. I'm not moving initially, I'm just kind of hanging over the cliff. All right, so in the end, this just comes down to my final kinetic minus my initial potential. And this is going to be a negative number because as the climber, I'm going to lose energy to the rope. I'm going to transfer energy. The rope's going to get hotter. Okay, the carabiner is going to get hotter, whatever. All right, so 1/2 mvf squared minus m times g times h initial. My final mechanical is all kinetic. My initial mechanical was all potential. All right, so when I plug in my numbers here, I'll have 1/2 times 72, the mass of the climber was 72 kilograms, times the final speed, which was 5 squared, minus 72 times 9.81 times 25 meters. Okay, so there's my energy at the bottom, 900 joules. Okay, and I'm going to subtract the energy at the top. All right, so I get a big negative number, and I only have, I think I have 3 significant figures here, so we'd say 1.68 times 10 to the 4, and it's going to be negative. Okay, glad to have the rope and carabiners and whatever else taking all that energy, because if I'd have kept it, I'd be a splat at the bottom. Okay, all right, how are we doing on number 2? How many people are done 2? Okay, I'm going to give you a little bit more time on number 2 then. Let's have a look at number 2 here. So we have a force of 150 newtons lifting a mass to a height of 5 meters. Okay, what's the work done on the mass by this force? So force times distance equals work, right? We're just going to calculate the work done first by going force times distance. We can put the cos of theta part in there, but theta is 0. Okay, and cos of 0 is 1. So right, we don't have to worry about that. So we've got our 150 newtons times 5 meters is 750 joules. Now, when I lift something, I do change its potential energy. If I lift it at a constant velocity, that's all I do. But in this case, I think I'm going to have a little bit of energy left over. right? So I'm going to calculate the change in potential energy just by going mass times gravity times height, or the change in height in this case. Okay, so that'll be 9 kilograms times 9.81 times 5 meters. All right, so I'm only changing the potential energy by 441 joules. Okay, but I did 750 joules worth of work. So the leftover energy has got to change what? Or the leftover work, I should say. The leftover work can't change the potential. I've already calculated that. What kind of energy is it going to change? The kinetic. Yeah. Okay, so whatever is left has to be the change in kinetic energy that the mass experiences. Okay? We know we did 750 joules worth of work, but we only needed this much to raise it 5 meters. Okay? That means that we accelerated it upwards 5 meters. Okay? Didn't just lift it, accelerated it upwards. So it got faster as well as higher above the ground. Okay? So all I have to do then to find the change in kinetic energy, okay, is take the mechanical energy, 750 joules, and subtract the potential. All I'm doing here, guys, is a manipulation of this formula. Okay, that mechanical equals potential plus kinetic. I'm just manipulating to solve for EK. Okay, so I'll have 750 minus 441. All right, so 309 joules of that, okay, ended up being kinetic. Okay, everybody all right with that? Okay, since I know the mass of that, would I be able to calculate the speed of this thing as well? Okay, I would. I could just solve 1/2 mv squared and figure out what v was, okay, for the end. All right, so question number 3 is saying calculate the net force that's acting on the mass. Okay, well, there's 2 ways to do that. Okay, the easier way involves this whole energy thing here. Okay, if I only wanted to lift this thing 5 meters at a constant velocity, this is how much energy I would use. Okay, but I've also got this extra stuff. So really, the net force is what causes the object to accelerate. Okay, we learned that before with Newton's second law. Okay, so could I use that 309 joules with force times distance to calculate the force? Okay, it's always the net force that changes the kinetic energy because it is the net force that causes an object to accelerate. Okay, an object can move with no net force, but it can't accelerate unless there is a net force. So the net force always changes the kinetic energy. Okay, so it's something we should probably write down somewhere. Okay, it is the net force that causes the change in kinetic energy. Oops, sorry. Okay, so that means the change in kinetic energy equals the net force times the distance. Okay, since I know the change in kinetic energy is 309, okay, I just divide that by d, which we were told is 5 meters, and that will give me my net force. I could go through a whole bunch of other math to calculate acceleration and do all of that kind of stuff, but this way is a lot faster. Okay, so when I do that, I should get 61.7 newtons. Okay, so tomorrow, to start things off, we're going to do a little quick kind of Newton's third law, a little activity, and then we're going to go back to this work energy theorem stuff. Okay, no quiz tomorrow, just because I haven't gone into energy enough yet to test you on it. So no quiz tomorrow, but there will be one Thursday.